Now that we've seen the derivative shortcuts for the logarithmic functions, I would like to take a look at a couple of example problems. So first up, we have f of x is equal to the natural log of x divided by x cubed. You'll notice in this case that we are dealing with a quotient of two functions, so I am going to employ the quotient rule. So quotient rule states that the derivative of a quotient will be low, d high, meaning the bottom function times the derivative of the top function, less high, d low, so the top function times the derivative of the bottom function, over the square of what's below. That'll be x cubed squared. Now granted, that doesn't finish the derivatives for us, but it does put them in a slightly easier fashion for us to work with. So this will be x cubed times derivative of the natural log of x with respect to x will be 1 over x, minus the natural log of x times the derivative of x cubed, that'll be 3x squared according to the power rule, over, if we square x cubed, that's x cubed times x cubed, that'll be x to the 6th power. Continuing to simplify the numerator, we can simplify x cubed times 1 over x to be simply x squared, minus, rearranging the terms, we'll call that 3x squared times the natural log of x, all still over x to the 6th power. At this point, you'll notice that there's a common factor that you could pull out of the top. Pulling out that x squared would leave us with 1 minus 3 times the natural log of x. This is all over x raised to the 6th power. Then, of course, we could reduce the x squared over x to the 6th and call this 1 minus 3 times the natural log of x all over x raised to the 4th power. Now, another possibility that you could do right away at the beginning of the problem is, instead of referring to this as the natural log of x divided by x cubed, you could also refer to it as x to the negative 3rd power times the natural log of x and employ the product rule instead. You would wind up with something equivalent to the same result. Next up, this time we are going with an unnatural log. This will be the logarithm base 5 of the secant of 2t. So in this one we are going to observe multiple uses of the chain rule. We're going to go with the outside-in approach. Our outermost function in this case would be the logarithm base 5. So f prime of t will be derivative of a logarithm base 5 is going to be 1 over whatever the input was, times the natural log of 5, all in the denominator. And then the chain rule says, let's multiply by the derivative with respect to t of the secant of 2t. This is where we're going to see the chain rule used once more. So derivative of the secant function, first part stays the same, 1 over the secant of 2t times the natural log of 5. The derivative of the secant function is the secant function times the tangent function, and the input to those functions will be 2t. The chain rule then says we'll multiply by the derivative of 2t, and employing the shortcut from a couple sections ago, the derivative of something linear is just going to be the slope of whatever that thing happens to be. Now, from a calculus perspective, we're done. From an algebra perspective, we can cancel out a secant of 2t with a secant of 2t and set this up as just one big fraction. So that would be 2 times the tangent of 2t divided by the natural log of 5. We'll go ahead and refer to that as our final answer. And one more example of logarithms in differentiation will be the following function. This is f of x is equal to the natural log of the square root of 1 plus x over 1 minus x. For this one, we are going to see massive uses of the chain rule. We will also see the quotient rule employed, as we do see a quotient in there. So let's start with the derivative of the outermost function, being the natural log in this case. So f prime of x is going to be 1 over the input to the function. Once again, 1 plus x over 1 minus x. And then the chain rule says let's multiply by the derivative of whatever was on the inside. Now, in anticipation of some more chain rule, I'm going to refer to this as 1 plus x over 1 minus x to the 1/2 power. That way we can employ the power rule at our next step. Additionally, back here, since we have 1 over a single fraction like this, I'm simply going to flip the top and the bottom, and we'll call this the square root of 1 minus x over 1 plus x. Again, reciprocal there. Then, employing the power rule to this part, that'll be 1/2 of 1 plus x times 1 minus x raised to the negative 1/2 power. And one more use of the chain rule says multiply by the derivative of the inside function. That's where we're going to see the quotient rule employed. Now, algebraically speaking, if we say negative 1/2 power, the negative means take the reciprocal of that thing. This part will stay the same. So take the reciprocal of that thing, and the 1/2 means that we'll be taking a square root. So it'll be the square root of the reciprocal of this thing inside the radical. Finally, we can employ the quotient rule over here. Quotient rule says, once again, low d high, the derivative of the numerator will simply be 1, less high d low, derivative of the denominator in this case would be negative 1, over the square of what's below. Now, once again, we find ourselves at a place where all of the calculus is done. Next up is for us to simplify this algebraically. So first off, we have a square root of something times the square root of something. That'll give us the square root of something, quantity squared. As such, the squares will cancel the square roots, and we'll be left with simply 1 minus x over 1 plus x. Then we'll have our term from the quotient rule left over. So, distributing the negative 1, at the very least, we'll have 1 minus x. We can use this negative 1 to turn this into a plus. So we'll call this plus 1 plus x, all over 1 minus x, quantity squared. Continuing to simplify, this will be 1/2 times 1 minus x over 1 plus x, times, this fraction will now become 1 plus 1, we get 2, and negative x plus x, those will cancel. We'll be left with 1 minus x quantity squared in the denominator. To finish simplifying this, I can cancel out one of the factors of 1 minus x as well as the factors of 2, leaving me with 1 over 1 plus x times 1 minus x, or stated more simply, 1 over 1 minus x squared. Now, with that in mind, this was about the most complicated thing that we could do with this problem. There is actually a much, much simpler way to approach this problem. Now, the approach is going to be, and I feel like I've probably said this a couple times in these videos, that a little bit of algebra can save us a lot of calculus. There are rules for expanding a logarithm, referred to as the product rule, or product property of logarithms, the quotient property of logarithms, and the power property of logarithms. Treating the square root as a 1/2 power, if your argument is raised to a power, you can bring the power down as a coefficient. So we can transfer the 1/2 power from the square root to a coefficient of 1/2. Additionally, anytime we're dealing with a quotient for the argument of a logarithm, we can change that into a difference of two logarithms, like so. Now, if I were interested in differentiating this function, it would require considerably less power and quotient rule and more constant multiple and difference rules. This will be much nicer. We'll go ahead and leave that 1/2 out front as a constant multiple, and then just differentiate the other two functions in here. Natural log of 1 plus x will be 1 over 1 plus x, and then the chain rule says multiply by the derivative of that 1 plus x, which will give us 1. Minus, same thing for the next natural log, that'll be 1 over 1 minus x times the derivative of 1 minus x. We can go ahead and use that negative 1 that we just got to change this minus sign into a plus sign. So 1 over 1 plus x plus 1 over 1 minus x. Now you might say to yourself, that's not quite the same thing as what we got the other way, but I guarantee you that they are algebraically equivalent, and we'll show it. So first thing I'm going to do is, since we have a fraction plus another fraction, let's establish a lowest common denominator and obtain that lowest common denominator for both of our fractions. The first fraction already has the 1 plus x, so I'm going to multiply top and bottom by 1 minus x to get our common denominator. Plus. The second fraction already has a 1 minus x. It still needs a 1 plus x, so I'm going to multiply top and bottom by 1 plus x. Once we have that same common denominator for both fractions, we can combine the numerators into one single fraction. So denominator is still 1 plus x times 1 minus x. We'll have a 1 plus 1 and negative x plus x. Now it's starting to sound almost identical to our last procedure by the time we got to about this step right here. Cancel the 1/2 with the 2 and expand the denominator, and we will arrive at 1 over 1 minus x squared, the same thing as what we got the other way. So regardless of which one of these ways you prefer, please know that once the calculus is done, there could still be algebra to do, and please always note that a little bit of algebra can save you a lot of calculus.